good to go? Super. So next thing we have to talk about is this thing here called the time constant. It's usually given the symbol tau. What is the time constant? The time constant of an RC circuit, a resistor capacitor circuit, tau, is equal to RC. What does this mean? First of all, we have to look at, let's have a look at a voltage time graph. Let's have a look at that exponential decay. It basically is given by this function here. We're fine with that. Now, what happens, I'm going to first of all have a look at RC. I'm going to do a dimensional analysis of RC. So, the units of tau are going to be the units of resistance, which is ohms, times the units of capacitance, which is farads. But I know the resistance is the voltage over the current, so that's going to be volts per amp. And I know the capacitance is the charge per voltage, so that's going to be a coulomb per volt. But hang on a second. I know a coulomb, or is charge is amps per second. So I know that that amp, so let's have a little look if I substitute everything in. So, resistance has got voltage over current. So that's going to be volts over amps, and capacitance is charge over volts. But I know that this is equal to amp seconds. So if I just substitute in here, I don't know if everyone can see this, volts over amps, that's going to cancel with that, that's going to cancel with that. The units of RC is actually in units of seconds. Right. So, have a look at this decay, decay. What's going to happen is, at some time, here, it will have decayed to 37% of its original value. If it's decaying, at some point it will reach that number. That time, let's see the significance of that time. So let's have a look at the function which describes the decay. We know that E, so the minus 1, equals 0.37. In other words, 1 over E equals 0.37, and that's just because E is equal to 1 over 2.71, whatever. So, what's happening here? If I look at this equation here now, if I rearrange that for V over V naught is going to be equal to E to the minus T over 4C. If this number is 0.37, in other words, if I've got 0.37 left, well then I know E has to be to the minus 1. It has to be. If this ratio is 0.37, well then I know that this thing here must be 0.37. And for that to be 0.37, I know that this bit up here has to be equal to minus 1. That's the only way it can possibly be the case. And the only way I can get that equal to minus 1 is if RC is equal to T. That's the only way it works. So every capacitor circuit or every RC circuit has got this thing called a time constant. And that is the time it takes for the voltage to drop from its original value, which I've just made 1 here, to 37% of its original value. Essentially what the time constant tells you is it tells you how quickly the capacitor will discharge. If I'm discharging through a really, really, really high resistance, it's going to be a really low current out of that capacitor. If I've got a really, really, really big capacitance, well then I know I've stored a lot of charge on that capacitor. So both of those things will mean the decay will take a longer and a longer time. So if those two quantities are big, I'd expect a capacitor to decay like this. What would my time constant there be? It would be this number here. If I've got low values of R and low values of C, I would expect my capacitor to decay like this. Excuse me. In which case, the time constant is this value here. What is that value here? Well, it's the time constant of the capacitor circuit. Does it have any significance? Of course it does. This value here, this value in seconds, is equal to the product over of R times C. R times C is got a unit of seconds. So that's what time constant is. I appreciate that was a little bit all over the place, difficult making videos. If you've got any questions on that, please ask me. Good, do that.